Let's jump right into this explainer, because today we're exploring something you're experiencing at this exact literal second, the everyday physics of heat. Now, we all think we understand it, right? I mean, it's something we feel constantly. But the actual mechanics behind how this energy moves, how it completely shapes our environment, and how we measure it, it's honestly mind-blowing.
Okay, let's dive into this. Here's our quick roadmap for today. We'll start with the unreliable sense of touch, look at how we measure temperature, and explore different types of thermometers. Then we'll cover the 3 ways heat travels, dive into conductors and insulators, and finally wrap up with the engineering marvel that is the perfect thermos flask.
So, moving right into part 1, the unreliable sense of touch, and why our bodies make for pretty terrible thermometers.
I want you to ask yourself a surprisingly tricky question. Can you actually trust your own sense of touch? Think about it. Let's imagine you wake up on a bitterly cold winter morning. You throw off those warm covers, you swing your feet out of bed, and you walk barefoot across your room. Try to really picture that physical sensation right now. Now imagine that bedroom has 2 completely different types of flooring. If you step onto a marble floor, it feels absolutely freezing to the touch, right? Like a shock straight up your leg. But if you step onto a wooden floor in that exact same room, it feels perfectly fine, maybe even comfortable. Well, here's the crazy secret. Both of those floors are actually at the exact same room temperature. No way, right? But the marble isn't actually colder. It's simply a much better conductor of heat. It's literally stealing the warmth away from your bare foot way faster than the wood does. You see, cold isn't an actual energy force. It's just the absence of heat. So what you're feeling isn't the real temperature of the floor at all. You're just feeling the rapid, aggressive loss of your own body heat. So if we can't trust our own skin, we really need to nail down the distinction between 2 words we constantly mix up in everyday life: heat and temperature. Heat is the actual moving energy itself. It's this dynamic, transferring force that always, and I mean always, flows from a hotter object to a colder one. Temperature, on the flip side, isn't the moving energy at all. It's just the exact measurement. It's simply the scale we've invented to put a number on that degree of hotness or coldness at any given moment. Which leads us nicely into part 2, how we measure temperature and establishing the perfect scale. Because our skin is such a terrible judge of reality, we rely on a highly specific device, the thermometer. And when it comes to human biology, 37 degrees Celsius is the magic number we're intensely looking for. That's the universally accepted standard normal human body temperature. It is the absolute baseline of our health. But, depending on where you live in the world, you might use an entirely different scale. 98.6 degrees Fahrenheit is the exact same normal body temperature, just converted into the Fahrenheit scale. It sounds vastly different, 77 versus 98.6, but the physical reality of the human body hasn't changed by a single atom. It's literally just a different mathematical language used to describe the exact same physical state. All right, moving on to part 3, different types of thermometers, finding the right tool for the right job. You see, you can't just use one thermometer for everything. Think about the strict, almost ritualistic procedure you have to follow to use a traditional clinical glass thermometer accurately. First, you got to wash it with an antiseptic solution. Safety first, of course. Second, you give it a sharp, forceful jerk. Why? Because that specific motion actively forces the internal mercury to drop below 35 degrees Celsius, which essentially resets the device. Third, you place it under the tongue for exactly 1 minute so your body's heat energy can transfer into the glass. And finally, you read the scale, making sure to keep it perfectly horizontal at eye level so you get a precise, undistorted number. Now, what's really interesting about this slide is the brilliant physical difference between the clinical thermometer and a laboratory thermometer. The clinical one has a super narrow range, just 35 to 42 degrees Celsius, because human bodies simply don't get hotter or colder than that without being in serious, life-threatening trouble. And crucially, it has this clever little kink in the glass tube. That structural kink traps the mercury, stopping it from instantly falling back down when you take it out of your mouth, buying you the time you need to read it. A laboratory thermometer, though, is a completely different beast. It has to measure everything from freezing ice to aggressively boiling water, so its range is vastly wider, usually -10 to 110 degrees Celsius, and it intentionally has no kink. This means you have to read it perfectly vertically while it's still completely submerged in whatever you're measuring. If you pull it out, that reading drops instantly. Okay, let's hit part 4. 3 ways heat travels, the fundamental movement of energy.
So how does this energy physically leave a source and move around our environment? Well, the first fundamental method is conduction. This is heat transfer that absolutely requires direct physical contact. Think about that extremely relatable mistake of leaving a cold steel spoon sitting in a hot cup of boiling tea. Slowly but surely, the heat energy travels from the hot liquid directly into the submerged bottom of the spoon. You can actually feel that energy migrating molecule by agitated molecule right up the solid metal handle until the part you're holding gets piping hot. That right there is the physical reality of conduction in action.
The second method is convection, which exclusively happens in fluids. And remember, in physics, that means both liquids and gases. Think of this as a dynamic moving cycle. When you boil a pot of water on the stove, the water closest to the heat source at the bottom warms up first. As it heats up, those molecules expand, they become lighter, and they actively rise to the top of the pot. This upward movement literally forces the cooler, heavier water at the top to sink down and replace it. This continuous, aggressive rising and sinking creates a circular current that eventually heats up the entire volume of water.
The third and final method is radiation, and honestly, this one is uniquely fascinating. This is the transfer of heat through electromagnetic waves. It requires zero physical contact. In fact, it requires absolutely no physical medium whatsoever to travel through. Just think about how incredible this is. The immense, violent heat of our sun travels millions of miles across the freezing, completely empty vacuum of space to warm our Earth, entirely through the power of radiation. It's a completely invisible, silent delivery of massive energy.
Let's roll into part 5, conductors and insulators, how we actually control the flow of heat. Once we grasp exactly how heat naturally moves, we can deliberately manipulate it using carefully selected materials. On one side, we have good conductors like copper, aluminum, and iron. These materials let heat energy pass through them effortlessly. That's exactly why the bottoms of high-end cooking pans are heavily coated in copper. It aggressively pulls the heat from the stove into your food as fast as possible. On the flip side, we have poor conductors, better known as insulators. These guys actively block heat transfer. We're talking materials like wood, plastic, glass, rubber, and even everyday air. These are perfectly suited for the handles of those very same cooking pots. Why does this matter? Because every single time you cook a meal, you're relying on this clever manipulation of physics to protect your bare hands from being burned by rapid conduction while simultaneously searing your dinner.
So the crucial point is, well, let me give you a winter logic puzzle based on these insulators. Why do 2 thin blankets keep you so much warmer than 1 really thick blanket? We usually assume thickness equals warmth, right? But it's actually all about trapped air. When you layer 2 thin blankets or wear multiple layers of clothes, you purposely trap a stagnant, still layer of air right between them. And as it turns out, air is a genuinely terrible conductor of heat. It acts as this powerful, invisible, insulating wall that actively stops your precious body heat from conducting away and escaping out into the cold room.
And finally, part 6, the perfect thermos flask, defeating heat transfer entirely.
And this brilliantly illustrates how human engineering masterfully combines every single concept we've just talked about into one perfect, everyday object. A thermos flask has exactly one job: stop your hot coffee from cooling down or your iced water from warming up. It's literally a fortress against energy movement. To defeat both conduction and convection, it relies on a vacuum chamber. Manufacturers literally suck the physical air molecules right out from between its inner and outer glass walls. Without those physical molecules to bump into each other, heat simply cannot travel through conduction or convection. They are completely blocked. Then, to defeat our third method, radiation, the inside walls of the flask are heavily coated in silver. This acts exactly like a mirror, taking that invisible radiant heat energy and bouncing it right back into your drink. It flawlessly neutralizes all 3 methods of heat transfer simultaneously, all inside a container you can toss in your backpack. So as we wrap up this explainer, I really want you to take a second and look around your environment. The incredible physics of heat transfer are happening right in front of you, continuously shaping your comfort, your food, and your home. But I'm going to leave you with a fun little paradox to ponder based on everything you've just learned. If a thermos is perfectly engineered to stop heat from entering and leaving, how does it know whether to keep your coffee hot or your iced tea cold? Keep your eyes open to the fascinating science around you, and as always, keep learning.